Okay, this is Honors Math 3, Unit 7, Objective 8. It's the last objective in the unit. I don't know that there's anything really brand new that we're talking about here, but we are dealing with a lot of word problems. And you do need the scientific calculator. Now we're dealing with exponential growth and decay, and some of the stuff is typed here. This is just I copied off 3 of the problems from the worksheet. This is problem number 1. And so you got the y equals a times b to the x. And if b is greater than 1, then we know that it is a growth function. And if b is less than 1 but greater than 0, then we know that it is a decay function. Okay, and much like when we were doing our functions the other day with our half-lives, a equals a sub 0 e to the kt, or negative kt, whichever way it was. This a sub 0 right here, that's the initial amount. Well, the a out in front right here is the initial amount. Okay, so without further ado, here we go, number 1. So, oh, and by the way, predictive formulas, exponential functions are really some of the most accurate predictive models, predictive equations, at least as long as there's not some major event, some catastrophic event, or some other major event that affects what's going on. But for 5 to 10 years at least, it's a very good predictor of what's going on. Sometimes longer than that, but anyway. So the median price for a new home in Fresno, California in 1975 was $58,000. Okay. In 1990, the median price for a new home was $113,000. Okay, and we calculate the growth or decay factor, the b value, by doing a ratio of those two values. So b is equal to, and you do the second data value over the first data value. So the second data value is 113,000. And then the first data value is 58,000. Okay. And so then we are going to be wanting to adjust it though, because right now that's a 15-year gap of time. And we want to be able to write our equations so that they are a yearly exponential function. And so what we do is we raise this b value, this ratio, to the 1 over gap of time. Now, since the time was from 1975 to 1990, then that's a 15-year gap of time, so we're going to raise it to the 1 over 15 power. Okay, so here we go. We're going to, by the way, okay, so anyway, the 113,000 divided by 58,000, that's like 1.9 stuff, but then I have to raise it to the 1/15th power. Now, when you do that, scientific calculators, now you might be able to get away with that without the parentheses, but a lot of times you do need the parentheses around the exponent. So, good idea to go ahead and just do parentheses around the exponent right there. And this is approximately, we're going to be rounding things to the nearest thousandth here, so 1.045. And so that's our, now notice how it's greater than 1, which makes sense because the first data value is at 58,000, the second data value is 113,000, so it is growing. So it makes sense, it should be greater than 1. And so 1.045, it's greater than 1. Okay, now we're going to write our equation. By the way, that was part A for number 1. Part B, we're going to write our equation. Now, it's always important to make sure you know what your start year is. And our start year is the first data value, which is 1975. So, valid for start year 1975. Okay, and so y equals a times b to the x. Now, you could also do remember how I had the a equals a sub 0? Basically, you could do a equals a sub 0 b to the t, because x is, it's time, really. You could do it either way, y equals a times b to the x, or this way. So a equals my initial value. What's my value at 1975? 58,000. 58,000 times that b value we calculated, 1.045 to the t. Okay, there's my equation. Okay, part C. Using this equation, what is the median price of a new home in Fresno in the year 2000? Okay, so the year 2000. So how does 2000 relate to the year 1975? Well, it's 25 years later. So we're going to be doing a of 25. In other words, function notation. So I'm inputting a 25 into my function a. So 58,000 times 1.045 to the 25th. And so really, we're just plugging in the calculator now. And so we have 1.045 to the 25th, which is a little bit more than 3, don't round it, times the 58,000. We don't round until the very end here. And so this is approximately 174,315, and we're talking about money, so 0.20. So to the nearest penny, there it is. And that was actually pretty accurate for the year 2000. So the year 2000, I'm going to plug in 25. What if we wanted the year 2022? I know that's not one of the questions, but what if I wanted the year 2022? Well, how does 2022 relate to 1975? Well, it's 47 years later, isn't it? So we'd be doing a of 47. So 58,000 times 1.045 to the 47th. 1.045 to the 47th. And that's almost 8 times 58,000. And we get $459,085.57. Now, that's a little bit big for the median price home in Fresno, California. So first off, two reasons why it's not very accurate. Well, first off, 2022 compared to the last piece of data, which was 1990, that's definitely more than 10 years away. And if you get beyond 10 years away, it starts to it's not as good of a predictor. You need to recalibrate the equation. Secondly, if you think back, and you've probably heard of this, but back in about 2007, 2008, there was quite a significant economic crash, and so that's definitely affecting things too. And so the median price home is definitely lower than that. Okay, back to the actual problem. The actual problem says part D, using this equation, what is the median price of a new home in Fresno in the year 1955? I mean, we can go back in time. Sure. 1955. How does 1955 relate to our start year of 1975? Well, it's 20 years in the past. Again, you know, it's like it's maybe not quite as accurate, but on the other hand, we're going back in time, and so we're going to be plugging in a negative 20. So A of negative 20, so 58,000 times 1.045 to the negative 20. And if you think about, you know, it's like on the growth functions, if you think about it, as you go back in time, as we go to the left, the function is getting smaller. And so that's what should be happening with this one. Okay, let's go ahead and try it. So we've got 1.045 to the negative 20, and it's like 0.4 something, times 58,000, and so it's approximately $24,049.29, which is not bad. That's pretty. It's probably a little bit high, but okay. Anyway, let's try number 4. Now 1, 2, 3, and 4. 2 and 3 are very, very similar to what we just did for number 1, and so you can go ahead and do that. Number 4 is also kind of similar. So we've got the A equals A sub 0 times the B to the T. Okay, so calculating my function here, initial population of 7 cells, so A sub 0, 7. It's doubling each hour. Now, hopefully you can just kind of see if it's doubling each hour, you can see that B is 2. Now, if that's not convincing you fully, then go ahead and write out, you know, it's like we've got time and the population, and times 0, you got 7. So after 1 hour, you got 14. After 2 hours, you got 28, and so on. And if you do the ratio, 14 over 7, say, and then raise it to the 1 over, well, what's my gap of time? 1 hour. Well, that's 2. So A equals 7 times 2 to the T. Now, valid for start time. They don't really give us an actual start time, so, but at T equals 0, if you plug in a 0, you can see we do get 7 bacteria. Okay, and T is in hours. Okay, so it's good to pay attention to that. How many cells are present 24 hours later? Well, we would be doing A of 24. 7 times 2 to the 24th. Shouldn't be that much, right? 2 to the 24th times 7. Oh, it's just a mere 117,440,512. Put the commas in the right places. And now this is kind of a simplified situation for the bacteria. It's a little bit more complicated than that, but bacteria is a very serious thing because they multiply so quickly. And this gives you a sense of why we do need to take things like that seriously. Okay, finally, the last one here, number 6. I included the little line, and so below the line, so below number 4, they're giving you the equation. We don't have to write the equation, we're just using the equation. And so if we take a look at the equation, A of t equals 80 times 0.727 to the t power. And t is actually in hours. If we read the equation, we see that the initial dosage is 80 milligrams. So during surgery, patient's circulatory system requires at least 50 milligrams of anesthetic, or else they start to wake up, and that's not good for a patient to wake up while they're on the operating table. You can see that the B value is less than 1, and so it's telling you that the drug, the anesthetic, is diminishing as time goes on, which is good. That's what you would want it to do. In fact, it's only maintaining 72.7% per minute after the initial dosage, as opposed to the first equation that we did, the 1.045. You've got the 1 plus 0.045. The 1 maintains value and the 4.5% interest growth per year. Whereas this one down here, the 0.727, is like 1 minus what is that? 273. So it's losing 27.3% each minute as it's going along of the initial dosage. I'm sorry, T is in hours. T is in hours. T is in hours. If it's losing that much per minute, that's not good. Okay, now this is a simplified problem. An initial dosage of 80 milligrams. This is if any of you ever become an anesthesiologist, then it's based off body mass index and lots of other things that you're going to have to do some calculations on. But we just simplified this problem some here. Okay, how much of the anesthetic is present in the patient's circulatory system 30 minutes after the anesthetic is administered? So this is part A. Well, 30 minutes, and T is in hours. So we're going to be doing A of 1/2 or A of 0.5 because T is in hours and they want 30 minutes. 30 minutes is half of an hour. So 80 times 0.8, sorry, let me get that right, 0.727, and now T is 30 minutes, so to the 1/2 or 0.5. Okay, so plugging that in the calculator then, so 0.727 to the 0.5 times 80, and after 30 minutes, you still have approximately 68.211 milligrams of the anesthetic still in your body, okay, which means that it's still safe to operate, and so that's good. How long can the operation last if the patient does not receive an additional dosage of the anesthetic? Well, they can keep on operating until they get to 50 without adding some more somehow. So, if A of t is 50 equals 80 times 0.727 to the t, and we can solve for t, so because it's safe to operate as long as they're still at 50 or above. So let's solve for how much time it takes to get to 50. What would we do first? Divide by 80, divide by 80. So if we do that, we get 5/8 equals 0.727 to the t. And we need logs. And it's base 0.727. And t is over here, and 5/8 is right there, and so we're literally just plugging it in the calculator now. Okay, remember how to plug that into the calculator. So that's log of 5/8 base 10 divided by log of 0.727 base 10. Okay, so log 5/8 divided by log 0.727, and I've got 1.474, and it's T is in hours. Okay, now I'm fine. If this was the test, you'd just get to leave it in hours. Now I know I did said, yeah, no, just leave it in hours, 1.474 hours. Find the half-life for this anesthetic. What does half-life mean again? The amount of time it takes for half of it to change or go away. So half of the initial dosage was 40. So if we put 40 over there and solve for the amount of time it takes for that, which is very similar to what we just did. So I get 1/2 equals 0.727 to the t, and log and base 0.727, and it's 1/2 equals t. And so t is approximately, let's see, log of 1/2, log of 0.5 divided by log of 0.727. So approximately 2.174 hours. Okay, that's part C. That's the half-life. Okay, now part D. This is actually pretty cool. Pharmacists and anesthesiologists multiply a medication's half-life by 5 to estimate when a medication is cleared from the patient's bloodstream. Now, it's not actually cleared, but you'll see what's going on. I mean, and think about this, half-lives. So after one half-life, you have half of the drug still in your system. So after 2 half-lives, you have half of a half, which is 1/4. After 3 half-lives, you have 1/8. After 4 half-lives, you have 1/16. After 5 half-lives, you have 1/32. So this is why they multiply it by 5. Because after 5 half-lives, you have 1/32 of what you started with, which, yes, it's still in your system, but it's really not affecting you anymore if you only have 1/32 of the drug still in your system. Okay, so part D, all you got to do is just multiply by 5, 2.174 hours, and we get, and I'm actually multiplying the longer version of it, so, well, no, I'll just do the 2.174. So 5 times 2.174, and I got approximately 10.87 hours. So the drug will be cleared from the patient's system in a little bit less than 11 hours. Okay, so finish off whatever we didn't do there for the notes, which is really just doing 3 of the problems from Obj8, finish off the rest, and let's make sure we're ready for the exam on exponential functions and logarithms.